Good evening, everybody. Welcome again to the consulate. We're delighted to partner with the Hungarian innovators. And I also want to welcome our friend and partner, our third partner is Eleanor Mészáros. She is the technology and science diplomat at the Vice Consulate of Hungary. So please meet Zoltán Egyed, who is going to introduce our speaker. Fantastic. I've been here watching already. It's a little bit like being in the Science Museum, Computer History Museum, actually. Zoltán Egyed.
Thank you. Welcome to our event because by the Innovators Club of Silicon Valley and Eva Voicing Honorary Consul. We are a non-political association of people involved in innovation. You can find our website at hungariansv.com. Our club is guided by two of us, my co-president József Patfaszky and me, Zoltán Egyed. Our speaker today is László Zoltán Buru, who has a very long experience in the laser field. We also have on the audience multiple physicists with direct and relevant knowledge of lasers. In case if you have some super deep questions afterwards, they might be able to answer them. So let us hear how lasers are forging our future. Please help me to welcome László.
Hello, everyone. So I'm László Zoltán Buru. This is my first show, so sorry if it's a bit bumpy at the beginning. I will try my best to make this interesting and a really an interesting experience without any boring details. We're gonna have a lot to cover. So let me start it immediately. So yeah, everything. We're gonna talk about lasers here today. So as you mentioned, László Zoltán Buru, I'm in the field for 12 years. I'm working for Applied Laser Solutions. Our CEO is right there. He's Frank Vaconi. He's my boss for 12 years. So I jumped into this field 12 years ago, and I was an IT engineer before. Now I'm more going towards lasers. It's a really interesting topic. As you will see, I hope it's gonna spark something into the people, into you guys, like how important is this for the future, because it's literally everywhere. We just not really seeing it. So first part to cover is what's a laser, what was before laser, how it started, when it started, and what was the first ever laser in the world. So laser is a quantum physics process. That's where it's, when you go deeper in it, it just starts getting more complicated. So we're not gonna go that deep. Albert Einstein, the famous physicist, already described this. And so the simple explanation for it is the incoming photon interacts with an excited atom or a molecule, and it will creating another photon with the same phase, frequency, and direction. You can say the light is copying itself in this process. Millions or trillions of a time in every moment or every second or interaction. So the most important thing here, but just it's just important to remember, is the emitted photon is the same phase, frequency, and direction, as I mentioned, because that's the difference between the light bulb and the laser. So that's why it's not just a simple light source. It's a special kind of light source. And here you can see the actual acronym for laser. It's this long word like amplification by stimulated emission of radiation. So before the lasers, there was this person, Charles Towns, in 1954. That's the time when he came up with this little experiment, and He literally did the same as we're doing nowadays with the laser, but he used microwaves. He used hydrogen atoms. It's called maser. That's the name of the actual device what they're using in atomic clocks. And even for today, this is the technology what they're using in satellites, radio observatories, because it gives you an extremely stable frequency and accurate and stable frequency. So even today, this is a really important stuff what's changed everything, and even today it's in every satellite, every radio observatory. This is their frequency, the baseline or their frequency master. Yes, sorry. So it's the same physics as a laser. It's just microwave. It's a different frequency on the electromagnetic space or the electromagnetic scale. The first laser, the first ever laser, it's made in 1960. So it's not that long ago. So if you just think about this is not like not like 200 years ago. So this is a pretty new thing. The first laser, but made by it's called a ruby laser. It's literally a synthetically grown ruby crystal, and they doped it with chromium ions. And the thing what's actually doing the laser is the chromium. It's not the ruby. The ruby is just a crystal structure to hold the atoms inside. And they use the flash lamp. This spirally thing it's like a flash lamp, like an old flash lamp. This long stuff on the like before LEDs. Before high power LEDs. They literally flash the tube, and that's made the chromium ions going to a higher energy state. And they had this thing called the striker, like a starter. This thing was called the reaction to drop to a lower level. Then the lasers, the new photons just came out when the chromium fell to the lowest state. We're gonna see this on the next slide. Other interesting thing to mention here, they're using this wavelength 808 nanometer to flash the ruby, and the laser itself that came out, it's only 694 nanometer. It's a deep red. It's a read, and they did it in huge research laboratory. So it's pretty close. So the next slide. We're gonna go over this really fast. This is just like basic physics for the whole process. What's happening? You have the atom, you have the electrons around. You're putting in energy. The electrons goes to a higher state. This is a really, if someone around this field know this, and when that energy level drops, so the electrons falls back to another state. Photons coming out. This is two different ways. It's called the three level energy state and the 4-level energy state, and it's just so like ruby laser did this. They went from level 1 up to level 3, and then drop back to level 1. This is the hard way. And nowadays, when we're going to talk about modern lasers, they're using this technology, so this way of exciting the atoms and stimulate it and pull out the photons, because it's just very easier to jump here between these 2 points. So do the lacing here because it's more it's more rapid. So hard way, easy way, but the modern lasers it works like this. Little bit about the electromagnetic spectrum. It's pretty obvious. This is what we can see. That's where X-rays, gamma rays, cosmic rays going. That's where radio and the longer waves going. Most of the lasers working around this area. So this visible plus minus a little here, plus a little here. So most of the lasers goes from 200 nanometers up to 10,000 nanometers, like 10 microns. This is a little diagram about lasers overall with different medium. As we mentioned at the beginning, chromium. It's chromium ion. It's right here. So this is the wavelength, what it will emit back, because every atom emitting different wavelengths. So some of the famous one, here's some CO2. Yeah, here's the CO2, 10 micron. So it's pretty, that's a pretty common type. That's what most of the people who ever heard about this hearing this, but you can see different gas and different mediums, different laser medium. It's called laser medium, and it's a very wide scale. There's a lot of options to make a laser, and you can pick your wavelength, and that's the most powerful thing about it, that you can make a laser for the exact required wavelength, because this one matters. When you have a material, every material have a wavelength what absorbs, and there's a wavelength what reflects. So you can tune in your process exactly for the material if you want. But just mentioning here, after a certain energy level, it doesn't really matter, because if you putting in so much energy, it doesn't matter if the material is going to absorb it or reflect it. It will absorb it after a while. So nothing stays reflected forever. A little bit of fundamental experiments. Here's we're gonna talk about some interesting experiments. Let's start with the basic. Everyone heard about this, the double slit experiment. This experiment is one of the clearest window into wave particle duality. And I would like to associate with, like in real life, I have the new experiment with me. We're gonna putting a black paper here, and you will start seeing the lines on the so the first of this experiment happened in 1801 with a regular light source, so not with a laser. So when the lasers came in, it just makes it more easier, more controllable, the whole experiment, and we will see it in a moment. So what's happening on the little experiment, what I will show you, we have a little slit, the double slit, the two little, it's a rectangular hole in a plate. We're going to shine the laser in. And what you normally think is you will see two red lines on the walls, because that's what the intuition. If you just thinking about the particles, you just see the shadow. So just see the two lines on the wall, but it will show something else, and that's when they realize that it's not a particle. So light is not a. It's in certain condition. It's a wave. So I don't want to go so deep into this. I'm not the specialist in the field, but it's getting from sorry for so yeah, it's a hard topic, quantum physics. If you understand it, you lie, because it's a thing what's really, really hard to understand. What's happening with the line? We have the crest and the trough of the wave, and when the two crests are meeting, it's doing a destructive interference. If the two trough meeting, it will doing a constructive interference. So it's getting brighter, or it's it's just going to zero, like no light on that spot. So let's see the interference line. I want to. I can put it here. Let's get a picture. This is oh yeah, here. I don't know how easy. Can you see it? Yep. Okay. Can you see the dots? You can go further away. So this is that famous experiment. I mean, it's just cool to see. So it's literally just a little slide with these two rectangular holes, and I'm just shining the laser here, and this is what we see. So it's and then we're gonna turn on if someone wanna see it closer. Oh, let me put this down. Just make sure no one really powerful. So next thing is, oh yeah, LIGO. Okay, so LIGO is the Laser Interferometer Gravitational Wave Observatory. It's an experiment with two observatories. What they built, they're using big lasers. It's to detect the gravitational waves. This is the famous in I think in 2012 or 2014. They did the first confirmed detection of two merging black holes. It was everywhere in the news, and it's confirmed Einstein projection about this. The whole theory of the time. As one of Einstein's theories, they just confirmed it. So the whole experiment looks like two giant 4 kilometer long arms. Both arms have a mirror at the end. They have a laser here, and what they're doing is yeah. So this is easier. So this is 4 kilometers. They're shooting the lasers, going into a beam splitter. They're changing the phases, and when it comes back, it can interfere. It can be a destructive interference or it can interfere. So that's how they see if it's moved. When the two waves are overlapping, it's destroying each other. Yeah. So and the displacement, what we looking here is this much meters. It's even so. So this distance is I think it's more than a neutron. So it's an extremely small distance. What we're measuring here. Sorry, I'm just having some trouble to. So this system measuring the unmeasurable thing, because this is smaller than a neutron. I think this is smaller than a neutron, if I'm right. And they did it. So it's one of the most complicated experiments in the world. This little drawing, what shows you the whole path, it's way more complicated than this. But this is just a simplified version of this. They're using neodymium vanadate laser. The neodymium here is the chromium, or is the trick, the rarer metal. It's just a really small percentage in the system, but that's what they're using for the lasing media to make the laser. Oh yeah, I mean, it's here. So that distance, it's 1/1000th of a proton. It's that small of a distance, but they're looking for when the space-time is waving or is stretching or contracting. So that 4 kilometer can detect that small of a change, because that's the only change what you measuring when when the black hole merging happening or any other cosmic event happening. So it's an extremely, it's unbelievably small distance. Yeah, it's these waves. What's happened with the merging black holes is predicted by Albert Einstein like 100 years ago. So he predicted this, that this will happen. And now they have actual concrete measurements that it happened, and the space-time moved, it's contracted and stretched a little bit. With the LIGO, it's just another thing where LIGO proved that with lasers we can measure the unmeasurable things. Next thing is the National Ignition Facility. It's here in Livermore. Probably some people heard about it. They did the nuclear fusion experiments in. They're doing it always, but they did the most famous one or the first working one in a couple of 5 years ago during COVID, something like that. These places have the most powerful laser in the world. Literally in every number, they have the biggest, the strongest. It's a nuclear fusion experiment. They're using a thorium capsule containing deuterium and tritium. That's the fuel for the nuclear fusion. And they're using this giant laser to this little pellet and ignite it. So do the fusion. So go to the temperature where fusion can happening, because you need a lot of pressure, or you need high temperature. So they're doing extreme temperatures here. I'm talking about 100 million Celsius. What happening down there in the middle? I will see so we will see a video about it, how the laser part's happening here, and how the laser is starting and how the laser arriving to the capsule to do the trick to start fusion. It's an infrared laser, but they're gonna convert it. I'm gonna explain this later in the video what's happening here. So as you can see, this is like it's called the seed laser. They're generating an extremely short pulse, and it's a 10 nanosecond pulse. So the pulse length is how much light can travel in 10 nanoseconds. And literally, this thing what you see, is the actual length of the pulse. So you have photons there, but you don't have photons before or after. So it's just a slab of a bunch of photons just flying there, because it's happening in an extremely short time. So they only turning on that laser for 10 nanoseconds. And it goes through a bunch of, it's called amplifiers. It's 3 football field long, and the laser bouncing back and forth. And that's where they putting more energy into the laser, as we see the 2 diagrams. When we're pumping up, when we're putting the electrons on a higher level, and it's dropping it back. So they pumping up these amplifiers on a higher level, and when the laser going through, it stimulates more electrons to drop to a lower state, and more photons are coming out, and those photons are in the same phase. So it's the exact copy of the photons what's going through the system, and they just pumping, and as you can see, it's getting bigger at the end, because the power density is getting extreme, and you don't have anything in the world what can reflect this. So there is no mirror what can reflect if you put it in a smaller spot. So your energy density is lower. That's why and actually it's square, because all their mirrors and their optics are square. It's just convenient for them. And as you can see here, they have 192 laser beams, and the 192 laser beams get shot into the target. And the actual target, The actual target is just, I will show you a picture, it's just a few millimeters in diameter. It's in there, that's the little capsule, and inside the little capsule, you have the uranium. And let me just stop it here for a second. And what's happening here? So they're not using the laser to start the ignition. They're using the laser to create X-rays, because when this laser hits, it's so much of an energy that you start putting energy into like gold atoms. It's just getting so the energy is getting so high that the gold atoms start emitting X-rays, and the actual X-rays what's collapsing this little pellet, and it's literally just exploding this pellet. And when an explosion happening, it's exploding outside, but it's also exploding inside, because that famous law in physics, whatever happening that way, it's gonna have an opposite force, and that opposite force collapsing this deuterium to a small space, and it's got the pressure high. It is hundreds of millions of Celsius what we talk about here. They're using an neodymium laser. It's also starting as an neodymium laser. And other interesting thing, when they designed this laser, they on the amplifier stage, they're using a glass called phosphate glass, and they bought out the stock in the world. They said if they have to repeat this laser, they have to build another one. Today is 10 years of the world production of phosphate glass. Phosphate glass is their ruby, if you remember the first slide. So the phosphate glass is their ruby. And it's just 10 years worth of the world own manufacturing capability just to repeat itself. And just one more little quick thing about this is before we, sorry, I just have to step back because it's a nice color. Yeah, it's happening here. Just a moment. Oh, yeah, just see. You see, it's red here. You start getting green, and you start getting blue. That's where the trick happening, because this light, what shoots the little pellet, it's UV light, but it started as an infrared light. And what they do here, it's called non-linear optics. It's a special kind of crystal where you shine in a light in an IR range. It's gonna doubling the frequency. So when you're doubling IR, you're going down to green. When you're doubling the green, you're going down to the UV range. And they're reaching at the last moment, they're having these big optics, and they just doubling that frequency twice and going into that huge energy level. This is really important because for plasma physics or plasma generation, infrared is, in this kind of physics, infrared is not a good thing because the frequency is not high enough. You gave too much time to the atom to do something. When you go down to the UV, it's such a high frequency that the atom really don't have a chance to react, to move it out, or I can say, yeah, something like that. So it don't have time to. It's short. The wavelength is extremely short. So let me think. Yeah, so literally that's happening here. Literally, backyards every other week. I think they're shooting because they really trying to build up this experiment to go away. Because this is actual fusion what they did. It's measured, it's proven, it's happened. This is just one way. So they have the other fusion experiment in France with the tokamak. That's a different type of fusion. This is called laser fusion. They're working on this way. If you make these lasers extremely efficient, this is probably something what's gonna work. But literally this whole experiment only lasts for a few nanoseconds. So imagine you have to do this like multiple times per second to create enough energy to make it work. So they still have, it's still like 5-10 years away, like always, nuclear fusion. But this is an approach. So this is a different approach what the tokamak and like when but the other famous experiments, the how it's called in French, the the ITER experiment in French, where like all the big countries dropped in the money and they building, and actually I think they put together almost the whole tokamak. So 5 years from now, they probably gonna start firing it up too. And so I believe this gonna, I mean, most people believe this is gonna save the world, because literally we have to, like, everyone should work on this fusion because it's important. And I put it here because of the laser part. So they also using lasers. So I said like a LIGO. So now we on the slides where I show you like how many places we're using lasers and how important is this. And only from 1960, this many things happen with the lasers. So let's go for the next one. Oh yeah. So that's the little palette here inside. That's the actual photo of it. In the last moment, they opening this, and they putting some helium gas in it. And this is this little palette. It's have an ice layer at the outside. So they have this cover on it to make sure this stays frozen, because they need the ice layer. Because actually the ice layer do the pushing. So that's what helps to make sure you can collapse it. It collapsing to the inside by the X-rays, what's emitted from the gold layers. But this whole thing is missing. At the end of the experiment, it's like, it's so much energy, it's completely gone. It's only lasts for a few nanoseconds. So next thing is the 300 FPS camera. This is just an interesting experiment. What actually even like people in the garage are able to do this thing. Oh, here is another thing what's happening. So they're shining the laser on the walls, not on the pallet. So the laser is to shine the gold, and then the gold doing the X-rays. It's also gold and some, I think, some diamond or some sort of materials. I think they're changing it, so they also changing the experiment all the time to just find better ways or better materials to do this. Yeah, so the 300 FPS command, they're using lasers as a light source. So that's why they're using the shine lasers in, and they're collecting the scattered laser light. They're using a single pixel camera. The single pixel camera have 1 picosecond per frame, and the light only travels 0.3 millimeter during the time. So it's a really short time. So LiDAR's working literally the same way. The videos are from Veritasium. It's a really interesting YouTube channel. Now it's a company. They doing interesting scientific videos, mostly to explaining extremely hard topics to people who just doing it as a hobby, or they're working in a different field. If someone interesting, I'm recommending them. They're doing a great job to spread science and, you know, spread the science in an interesting way that it's getting interesting for so many people, and you know, it's not just boring like numbers or whatever. I think they're doing the best job on YouTube now. So here's a video of what's happening. So they having the single pixel camera, and they're pointing into that corner. They're shooting a laser beam. They're counting how many photons hits the sensor, and and on what time. And because the sensor is so small, and they only got a few photons there, because it's just one short laser pulse, they sampling the same place multiple times. The trick here is the scene and the laser pulse have to go the same way every single time. So the timing is critical, but that's where laser coming in, because you can time it extremely precisely, and every single frame, when they do the frame, they can do the same, the same amount of photons. They're putting the same amount of photons onto the scene. And there's some actual videos on the next one. So they're sampling it 6 times. they're gonna average it out. That's how they're doing a single pixel, and you can do as many as you want pixel wise. So this is an actual video of a laser beam shot into a room, and that's the actual light. That's the actual photons, how they're traveling through the scene in 8 nanoseconds. So you can see light travels. Yeah, so the next one, the same. Oh yeah, so this is an actual, it's made by a guy, I think at MIT. I think they made this at MIT. It's a fish tank with water. They have 2 mirrors inside. And they move the cameras, so it's like an extremely long, like, it's really hard to make this because they captured it in different angles, and you can see the laser pulse going in, and this one, this is also interesting here. I want to stop it. So that little thing there, it's called diffraction grating. It's a little glass piece with a bunch of lines. Remember the double slit experiments. It's and over here you can see the different modes of the light. This is like the different angles. The same as we see on that little experiment. Each mode is a specific angle that light constructively interferes. So here's another one, a little flyby. And it's cool to see the light moves. So oh yeah, so now we are the microchips. It's gonna be easier for me. This is also, they're using lasers here in a really specific way. What we're going to talk about here is this. Some people saying is the most important machine nowadays. It's so important. European Union and the US have restrictions on this to make sure it's never going to go to China. And it's the actual lithography machine. This is the microchip making machine, but they just used to make the patterns onto these wafers. I'm gonna give you a few. You can look at it closer. This machine says, I'm pretty sure everyone heard about Moore's law. When every other year transistor count's gonna double on a chip, but actually it stopped at 2015. And then when ASML came in and saved the world, saved the law with this machine and technology. And the first proposal of this machine was from 1990. So it literally took 36 years to the world they know what they have to do. They know what wavelengths they have to do this 13.5 nanometer. Because if you remember the scale where the UV is happening, this is UV, but if you go lower, it's gonna be X-ray. And you know what's happening with X-ray? It's bad because it's going through on most of the things. So it's so hard to reflect. It's hard to reflect. So you really need something that you can still reflect a bit. But that's going to be another, we're going to talk about that part too. So back on the machine a little bit. So this machine only do the lithography. It means you have your pattern, you have a light source, you're just making a bunch of photos. It's like the old time photoing when they're using the dark room to make the photos. They're shining down through a negative. Same thing happening here basically. So this is one step out of the 250 what they need to make a microchip in a fabs, in that famous fabs. You know what they're building in the US finally. They're building a lot. TSMC. TSMC is the most famous. I'm pretty sure people heard about that. I think in 2025 or 2026, Intel bought all the machines from ASML for that year. So literally you're not able to buy. I think it was last year or this year, but it was a shortage on it because Intel just bought all of them. And the price tag on this machine is $400 million. It's like a public number, and it's only doing photos on a silicon wafer. It's doing nothing else. We are nowhere near to the transistors and stuff after this. This is just literally shining light on a film. Yeah, this is the actual size without the cover. So it's not the nice cover, but there's people here. It's crazy complicated. It's like we have complicated machines in the world, like CERN in Switzerland. I think this is the most complicated now. I think this is the first place now. How complicated is this whole system? So what's happening here? It's the most important thing is how are we making that light? How are we making that 12.5 nanometer light? 13.5 nanometer light. That's where the trick happens. That's where lasers are coming in, because you have LEDs, what can make different wavelengths. But this short wavelength is a special, and they're doing this wavelength coming out when plasma events happening, like nuclear fusion or in a star. So it's really you cannot just make a light source, a flashlight, but make like 13.5 nanometer. You have to make actual plasma, so actual little sounds to produce these wavelengths. And the technology what they're using is called laser produced plasma. This is one way to make plasma. Other way is just to use a strong electric field and make plasma. That's when it's not scalable. So they find it out really fast that they have to use this laser produced plasma because they have to scale up this whole system. So what's happening here is, let me show the video first just to walk through, and then I'm going to explain just a few little details here. So this is the actual video online about their newest machine. It's called NA EUV. It's high NA, high numerical aperture. They can make more chips at the same. They can make it faster. So they're developing this. I think this is the third generation of this machine already. And it will walk you through when they're shooting a laser. The laser is a CO2 laser. It's a nothing special laser. But what they do here is they're dropping thin droplets, and they're shooting the thin droplets with lasers and making the plasma, and that plasma creating that light, and then they're reflecting that light. That's where the pictures are, and those pictures are transferred down to the silicon wafer, and that's how they're making the patterns of the actual transistors. Yeah, there's the wafer. So they're putting a new one, and this is like some measurement. This is not the actual, and the EUV happening here in crazy speed. So speed is everything here. You have to make a lot of microchip in a short amount of time. So I want to go back to the thin droplets after this. So literally, this is the whole system in short. Let me go back. I'm like 70% in the. It's good. I'm still good time-wise. Sorry. Okay. Thank you. Oh yeah. I just wanna go back to my. Yeah. So this little thing what's happening. They're dropping these plasma droplets seen on the video. That drop, it's 25 micron in diameter. Your hair is 80. So you're like, how small is that little drop? It's a drop of tin, the actual SN in the periodic table, the actual metal. They're shooting with 250 kilometers per hour. It's 155 miles per hour. And they're doing 50,000 drops per second. And they have to shoot the drop 3 times, one after another, because the first shot making the drop flat, the second shot making it hot, and the third shot was striking the plasma. And they're doing this 50,000 times per second, and they saying they never missing a single drop. They never missing a drop. So it's crazy what they achieved there, because you just imagine it's a third of your hair. You have to dropping it 250 kilometers per hour, and you're shooting it with a laser beam. So it's crazy if you think about it. Oh, and everything happening under vacuum. So that's just actually it's getting it more easier, because you don't have to worry about the drag or anything. They're using a 20 kilowatt CO2 laser, but it's a pulse one, so the laser power is actually megawatts. So it's like they're shooting amount of power here to make the plasma, but it's only 25 micron in diameter. So it's a crazy small. So the EUV output, the actual extreme ultraviolet is 600 to 800 watts of light coming out. But the next generation, they want to go like over 1,000. But this is actually 13.5 nanometer wavelength. So it's, if you go, higher the frequency, shorter the wavelength, you packing in more energy. You have more photons. You have way more energy than a regular infrared. Yeah, but so this is 13.5, and from 0.01 nanometer to 10 nanometer, that's where the X-ray is. So we are so close. So this is just right on the edge. It's so bad for you. This one is already it's also bad for people. So that's not something where you can see. So, and this is called the collector mirror. So laser shooting in the mirror, shooting in the center of the mirror. They dropping the drops. They're making the plasma, and they're collecting the light with this curved mirror. This mirror have to be flat. It's so flat that it's the largest defect on this mirror is 2.3 silicon atom thick, and it's made by Zeiss. So Zeiss people are, the Japanese optic. I'm pretty sure people know the company. They made this work. German. Sorry, German. Okay. Pretty sure Japanese people did something important here. So as I mentioned, there is two versions. It's called one of them called low NA. Another one is called high NA. That's the new version. It's bigger optics. It means just bigger optics in the system, so they can collect more light. They can focus down more. They can make smaller details. So the collector mirror, just a few little nice. Just about the flatness of this. So this mirror is, I think it's about like 1.5 meter in diameter. If you size this mirror up to the size of Germany, the largest hill is 1 millimeter. But the high numerical aperture version, if you size this up to the size of the Earth, the largest hill is gonna be 0.25 millimeter. It has to be that flat, because when you start going to that extreme frequencies in the electromagnetic spectrum, everything gonna absorb it. So in this system, don't have any lenses. So there is no lens. It's only mirrors. Because if you're putting a lens here, and if you wanna shine through a clean glass or anything, it will absorb it. There is no way that this thing goes on. Even the cleanest lens gonna absorbing this. Because it's so high energy, it will catch on everything what you put in. So it's only mirrors, as we see in here. So this is all mirrors. So laser happening here, the pin drops, they're shooting out, and that's how they're shaping the beam and focusing and do the stuff. And up here is the negative. It's a reflective, so they're not shining through as when you do the negatives with the photos. They're reflecting it. And one interesting thing about it here, but when I talked with Zoltan about this, he mentioned the mirror, like they're putting a lot of metal in there. They're putting tens of thousands of drops of metal here, and it's vaporizing in vacuum. And you need that mirror to be really clean. And they actually have issues before. They had issues at the beginning. So just to make everything fun, this is under vacuum or extremely low pressure. They also have this little chamber where the laser happening or where the light's happening, they're shooting through hydrogen in 360 kilometers per hour to flush out the tin, the remaining particles of the tin atoms, because it's combining with hydrogen, and that's how they're flushing it out. And after a while, they also figure it out. The mirror still get dirty, and they don't. So this light destroys everything. So this light started a little bit destroying the mirror after a while, even the clean mirror. And they figure it out just by an accident. If they adding in a little bit of oxygen, it helps to repair the mirror. So that's how they maintain the mirror. So this whole system, when it's running, because it's $400 million, it have to run for a year without nonstop. So that's when this system starts working. If you can run this in a year, hundreds of wafers per hour or per day, because that's one of the metrics of these systems, of these semiconductor machines. How many of these you can push through? I can show you this. I can just, everybody can practice this. Put it around. So one of them is clean. There's nothing in here. This one already has the panels on it. So this is already like transistor. So this is the small version. They used it before, and they're still using it for some really special applications where really they don't want yield, they just want some special one. And the machine what I showed is using this one. So this is a blank wafer. This is silicon. It's actual sand. It's cheap. It's everywhere. We have a lot, so there is no shortage on this.
300 millimeters.
Yeah, it's 300 millimeters. This is the standard. And when they're doing this, they're melting it down. And I don't know if who went to the Intel Museum? Have you ever been Intel Museum? Someone? You remember the big gray block? So the big gray block is the silicon block, the ignite. They're pulling it out. It's a single crystal, so the crystal structure is almost perfect. And they're using a saw, so they just literally like dicing as a quick salami. So it's the same way. It's literally the same way. And so here's a 300 millimeter version. It's also has chips on it. So this is already every single of these squares is a chip. At the end, you can check this a little bit closer. So okay. Please. Just want to put the air out from under it, so it's not going to fly away. Okay. Don't touch it, don't touch it, please. Don't touch it, don't touch it. It's hard to clean. I just wanna keep it clean. I'm gonna put in. I have to clean it today, but it is fragile. It's fragile. It's like glass. Clear glass. So, and here's another one. It's called 450. They're not using this into this machine, but they're using this for the. It's called the dumb chips. So this is for the cheap chips or the analog chips, like for like Texas Instruments. So there's a company called a little company called Texas Instruments. They
I don't think we make 450.
no, but for the dumb chip, they doing the for the dumb chip, the analog, the cheap.
So who's manufacturing that? Because I'm not aware of a single fab that we would have.
Yeah, but Texas Instruments made a proposal that they want to switch to the 450 and do it in mass quantities here in the US.
Oh, I'm sure they would.
So that's the only way to able to make this feasible, economically feasible, to move the dumb chip manufacturing to the US. You have to make a lot of them in one shot, and you don't need the accuracy, or you don't need that fatness, or you don't need anything because it's analog chips. But in every single battery in the world, like every single stuff that have electricity in it, it's gonna have a Texas Instruments chip in it. So it's everywhere. It's still so we have these high-end chips, all the AI and stuff, but still the battery, the power supply, like everything else down the line still needs the cheap chips, the cheap versions of the chip, and we still have to manufacture that one too, not just the high-end, chips. Sorry, I mean, let me just go through this, make sure. Okay, so that's pretty much that's it. So that's where the wafer is. And this is the little patterns But they're putting a photoresist on it. So it's the same way as when you do the photo, how it's called the darkroom, what they do there when they're developing the photos, you know, they exposing the negative. What we have here. Oh, I already showed this. Yes. Sorry. Yes, I already showed this. So this is ASML's machine. It's a company in Netherlands. And actually, I think the laser, it's made by Trump. That's another half European, half American laser company. They did the laser source. So there's a lot of companies work on this technology. So we're gonna move to the industry a little bit. It's gonna be a bunch of interesting video, like how many places we're using lasers. Sorry, I'm just missing my, yes, here. Oh yeah. So back on the EUV a little bit. Sorry. So just one more thing to mention, like China. You have to mention it. You know, China won this machine badly because for the high-end chips, you need this lithography technology. There is no other way to make this work. And actually, when ASML started designing this machine 36 years ago, they proposed a way to make the EUV light, the extreme ultraviolet light. And there's another way, when they're not shooting the drops, there's another way. They have these cylindrical shaped rollers, and they're rolling these guys into molten tin, and they're shooting the actual rollers with lasers. And that's like another way to generate the EUV. And actually, China actually doing that. So they're testing their system. So they have their own version of this, and they also producing extreme ultraviolet light because that was the answer to make this work, because X-ray is just they tried X-ray at the beginning. Really, like this is the point, the 13.5 nanometer where you have to go. And also, like another interesting thing, you're seeing like they're talking about 3 and 4 nanometer chips, but they're using 13.5 nanometer light. If you have a gap, what's 10 nanometers, 13.5 nanometer light cannot go through that space, because your limiting factor is if the gap has to be bigger than the wavelength. So how you make 3-4 nanometer with 13.5 nanometer light? So they doing this for a while, and they did it before when they start stepping down the trace width, the transistor size. They only had like 120 nanometer light. They just started overlapping, and it's just a bunch of more steps in the system. But let's say this is your 100 nanometer, you're putting another one here, you end up with a 50 nanometer. And when you're 50 now, you're gonna do another overlap just a little bit over. So you start cutting it down. So that's how they step down that. They also use like different focusing technique, but that's like one of the technique to make it smaller, make smaller feature than your wavelength. And also NVIDIA, it's a big part of this thing, because that's where AI came into the picture, because you're making so small features that they invented a new way to do this. It's called computational lithography, and they're using AI and all those high-end systems to simulate how the light works, like NVIDIA's ray tracing. They had the physics simulation over there, and it's an extremely important thing to make this work, because you want to make a circle, you cannot just shine it to a circle shape, because it's not going to be a circle, as you see on the double slit experiment, because normally you're expecting 2 lines, but it's not 2 lines. It's a bunch of gratings on the wall. So same thing happening here, but it's just everything is just way smaller. So they're using AI to figure it out how to build a negative to end up with the shape what they want. So back in the industrial thing, the industrial laser use, that's like pretty much everywhere now. Normally they're using fiber lasers. It's I will mention it in a few moments for a few sites. They're using lasers for cutting, drilling, welding, marking. The laser welding, it's a thing what's just coming out now. So in my opinion, I mean, we see the industry, laser welding is one of the fastest growing things now. And I will show you a few videos why. And also, these three metals, these three rare metals, because we know the political situation everywhere in the world. Like some big countries have this, all this, and it's extremely important to make lasers. So here's another part of the industry where these rare earth metals, it's not just important for the batteries, it's also important to make lasers, because there is no lasers without this metal, because those are the chromium. So those are the lasing material, the lasing metals. Okay, so yeah, so fiber laser, everybody familiar with the fiber internet, fiber communication, we shining through light in a waveguide with the internal reflection. This is a regular laser. You have a resonator, you have two mirrors, you're putting some gas in it, you're applying high voltage, electrons going up. What?
Ionizing it.
Yeah, ionizing it. Electrons goes up and they fall back, photons coming out. You have two mirrors, so you start bouncing back and forth. And this mirror letting a little light out, because you need the little light in to keep the ionization in level. And that's how most of the laser works. You have two mirrors at the end. You're doing something in the middle. What's going to create photons in same phase and same frequency? You're just pumping it up. So you're putting a bunch of photons in there and you're letting a little one out, a few photons out. Fiber laser, in other way, it works pretty similarly in one type, but your resonator, it's a bunch of fiber, like the same fiber where your internet goes. But this fiber have some of the neodymium inside the fiber. So in the outside of the fiber, they have these rare earth metals, and they literally just flashing that. They literally just making a bunch of flashes inside the glass fiber, and as that light bounces, they're using that light to put the electrons on a higher state, and when it's falling down, there is more photons happening. So that's why it's called pumping in the energy. So they're pumping in the energy into this fiber. It's like long, it's like 20 kilometers of fiber, like coiled up there. It's a special kind of fiber. They also have like mirrors, the same as there. So this is how most of the fiber lasers work. This is a really important thing, and also it's cheap, and like literally everything now it's working like this. So every laser, this is the base, this is every laser, and it's creating infrared light.
Can I add something to this? Yes. Okay, so the laser output, how much of a laser is a function of the diameter and the length of the resonator. So a long time ago, the upper picture, the CO2 lasers that basically filled with certain gases and some gas mixes, because the chemical reaction of the gases give you a higher energy level when you ionize them. It happens at 25,000 volts. So it's, you don't get too close to it, you can get zapped. And the fiber laser is basically a same equation, except it's 20 kilometers. Just screw it up, and it's easy. It doesn't have to be straight because the fiber makes such a way that it bounces back. So it's like a waveguide. And that's that most reliable lasers are fiber lasers, as I can explain it. And they have very good power output, but the whole output is maybe 3 times the diameter of your hair. So it's much more usable. And again, I don't know, what is too much, but really, when you look at the lights, it's our combination like a rainbow. All colors are here, so they block each other out. But the laser has one single frequency of that spectrum, and different materials to a single frequency, they react differently. So you can evaporate them, cut them, or ablate them. And that's where the industry comes in. So basically, the material energy is so much pumped into the material, just disappears. So therefore, you can drill, cut, whatever you can do out. So anyway, this is laser his expertise is to develop these applications.
Yeah. So, yeah, as I mentioned, but over here we're using high voltage or RF, so RF frequencies. So you have to use high voltage or high frequency RF to make this, to excite this gas. On the lasers, you're literally using light for the same reason. So just for the same thing, you just pumping in photons, and those photons are making that rare earth metals excited, and that's where the actual laser coming out. So that's the thing. So the flashing lights are not the same wavelength as what the laser was coming out, because these flashing lights are for the rare earth metals. That's not the actual, and the rare earth metals doing the laser. That wavelength, what the laser gonna. So it's exactly the same. You have a bunch of diodes. This is laser diodes. It's your regular, on the shelf laser diodes. So it is the same. It's also fiber laser. It's just a special case. You have a pulse. This is a piece called pulse laser. You have a laser pulse that's going in, and they also flashing this bunch of fibers. And when this one single pulse coming in, that's one doing the stimulation, and that's when the other photons from this fiber joining to this guy, and it's going to the next stage. You're also pumping up the energy in this fiber. Your other wavelength coming in, it's also picking up these photons, and that's how you ending up with a lot of energy. So from now on, it's just little videos for the C. So you can see it's a fast video with some laser coming, how it's working. It's a really thick piece of the steel. This is real time. So this is real time with I think it's a 10 kilowatt, something like that laser. This is still, and this is the speed. And this is not a big deal nowadays. It's everywhere. Everyone uses it. It's affordable. So this is not like a really. So forget the plasma cutting or whatever, because lasers are now. This is also some laser welding. That's where I want to mention the laser welding going to be the next big thing, because they have when they doing the sparks with the conventional way of welding, but laser welding came into the picture with fiber lasers. It makes it so easy that even with a person with zero experience can pick this up, press 2 buttons, put down 2 pieces of aluminum, pull the gun and just pull, and you can weld aluminum. That's considered one of the most, the difficult to weld. And I'm pretty sure welders out there getting really nervous. I hope they're getting nervous, because this is a thing where this whole laser welding came into the picture, and you don't need you have 20 years of welding experience. Get the fiber laser welder, and you can just, yes?
Can you weld titanium?
Okay.
Can you weld titanium with this?
Yes. Anything, but that's like atmosphere. You need special atmosphere for the titanium. So so the interesting thing about you can weld these similar metals. That's impossible with actually you can do with TIG, but you need skills for TIG. Like TIG welding is the king of the weld. If you can do TIG welding, you are the star. MIG welding is sort of, and the electrode welding, when they do the shipyards, these big sticks, they burning the sticks in, they molting the metal, and that's the old way. And just talk about the energy here. Like lasers are way more efficient than that other. You're making less smoke. It's easier to use. I mean, literally with zero skill, you can weld aluminum. And you can get that like this for like $10,000, $8,000 for home, and start weld aluminum. And really don't need skill. Welding and literally you can weld anything. And with lasers you can weld glass. Not with this, but with laser you can weld quartz. You can weld actual glass together. Sorry, I'm just. So in the ship industry, I don't know which shipyard, but some of them are already trying to switch to laser welding. When they do that huge, the shipyard, they're making these extremely large, size of the ship with a bunch of ribs in it. So they're having the outside shell and they're having these reinforcement ribs. And because of the laser welding technology, they can decrease the thickness of the ribs in the ship. So they need less metal because laser welding is so accurate and so much comfortable. You don't need that big chunk of metal. And actually you concentrating your heat more into one space. So you have less. So not everything gonna heating up. It's so concentrated on that little spot that you don't need a big chunk. So actual newer ships gonna need less steel for the ribs, for the reinforcement, because the only reason before it was because of the weld, because you're burning in, you need mass to spread the heat. Otherwise, everything gonna start wrapping. And there is some shipyards who are already working on this technology to switch to laser welding because it's just way easier and non-skill. So here's the video. Here's the video of this is aluminum or stainless steel. I'm not sure. Yeah, it looks stainless. It looks stainless. So they're just gonna tack it to make sure it stays there. And this is a wire feeder. So this guy in the wire, and the laser is coming from here. So this is the actual wire, like on the MIG welders or TIG welders. Like that's the filler material. Literally, what the guy is doing is putting in there, pull the button, and pull it. So if you have the skill to pull something in constant speed, you can make this. And it's literally just a setting in the laser. So these lasers nowadays, you can buy it under $10,000. You type in your material, you type in your thickness, the laser do everything. You just put it down, push the button, and pull. No thinking needed. It's extremely reliable. It's way more controllable than anything else. So, as I mentioned, they're doing like dissimilar metal welding. That's a really big thing when they have two different kind of metals and they welding it together. Also, there's some inspection parts of this. So they do the laser welding. Just imagine this is the same as we've seen before. This is just a different configuration. It's not a handheld laser welder. So they're melting the material. So they're putting a lot of heat there. There's no filler wire here. And this is a really interesting technology. A few companies doing this. During the weld, you have a little bit of molten material here. And they're doing also with laser, surprisingly, they're shining in a different wavelength into the same beam path. And that wavelength, the molten metal is transparent for this wavelength. And they're literally scanning the bottom of the weld in real time. We've seen this system. You can buy this. It's on the market. You literally weld with the lasers. You can have a continuous 3D scanning inside the molten material.
A video.
So you will see all the, you will see how deep is your weld, because that's the most important thing of the weld. Like one is cracking, another one is how deep you went. And this is like a real-time data. And you can go back. You still need to check for like crack testing, but that's like normal for most of the weld. But it just removes another factor during the welding, because you can check the depth on the fly. And when you do this, imagine you automate this, you can feed this data back and you can make a perfect weld every single time, because you're feeding back your depth data. Like slow down, go faster, slow down, go faster. So it's it's a really, I mean, that's going to be the experience. That's my bet is that the laser welding is going to be the next big thing that's going to change. It's going to make a lot of welders' life hard, really hard, because you have 20 years of skill. And so with this regular laser welder, what you can buy anytime, you can weld 6 millimeter thick. It's like 1/4 inch stainless steel. With the handheld, what we saw in the video, it's up to 6 millimeter now. Yeah.
Actually, there was a Hungarian company who wanted to order from us a system like that, welding 10 millimeter thick stainless steel. And the reason why we didn't make the machine is because the Ukrainian war and the Russian bank was forbidden them to finance it. Otherwise, we would better want to have indoor system designed by Zoltan and our team.
Yeah, so
Yeah.
we have some we're gonna have some business with some company where they want like 10 millimeter. That's not a handheld. So this is not a handheld laser welder. So with a handheld, you can go to like 6 millimeter, because after that power is getting so strong that it gets so warm just standing next to it, because infrared is shining back. So, and the cool thing is about laser welding, you don't need the dark glass, because for welding you need the dark glass because the light is so intense. But for the laser, you only have to filter one certain wavelength, 1000 nanometer IR. So literally a laser welding glass, if I wear it here, I can see everything. It's not dark. It's not like, the welder's glass, it's have to like go to like dark, and stuff. Laser welding glass, it's literally a green piece of glass, and you can see everything perfectly. And there is less smoke, less. So there's all benefits. And now we're down to 6 millimeter, but with this technology, you can go whatever thickness you want, as big as your laser. But lasers up to like 40, 50, 100 kilowatts. So, the limit is the sky now with the lasers. With this fiber laser technology, it's really important. Like, this is all about fiber laser. So next thing is the additive manufacturing, like 3D printing. They also using lasers. So this is one of the type when they're using this metal powder. It's a metal powder here. They're having a laser up there, and they're literally drawing the image on the metal powder. They're putting in another layer of metal powder. They're drawing the image again. So 3D printing with lasers, like metal 3D printing with lasers. It's melting the metal where the laser touches, and that's how they building the layers. And actually they can do this with copper. So they can do copper and all sorts of alloys. They are using this in the industry. So it's a really big thing already everywhere. Like every company doing space stuff using this technology, because it's cool. But it's also happened because of the lasers. I have a few more. So that's oh yeah, this is also 3D printing, but it's an interesting way to 3D print. So what we see here is they're pushing in metal powder from these tubes on the side, and they're shining the same laser as laser welder have. They're shining the laser here, and they just literally blasting vaporized metal, like metal dust. And when they do that, okay, why is that?
Is it just going to be spitting metal droplets?
Yeah, so it's literally but in there, so they can build up the actual part without having that hole. On the previous video, you have all that leftover powder around it just to hold everything together. But that's a good thing in certain cases. But in certain cases, they can just really start on a flat plate, and they just build up like a cone shape for like mostly like rocket applications. It's a really easy thing. Sorry, technique just not working. This video just not working. Okay, like this one working. Okay, I don't know what's happening here. Okay. Oh, okay, unfortunate. Okay, let's go to the next one. This is also interesting. This is also laser. What you see here, this is water jet. This is a water jet. You heard about water jets. They're using water jet. They're putting some sand in it. They're cutting stuff. So what they're doing, they have this water jet. This is a hair-thin water jet, and they're shining the laser inside the water. So imagine a hair-thin 50 micron jet of water, and they're focusing inside the infrared laser, and inside the water jet, laser bouncing. It's called total internal reflection. If you pick that angle correctly, the laser never goes out from the wall. The same when you shine the laser into the lake, and it's just follows a different angle. That's a video. I hope it's gonna work. Oh yeah, it's working. The water is just a waveguide, and the laser do the cutting. What's cool about this, we will see on the next one. So this is just you see an extremely thin metal piece. This made by a Swiss company. You cannot buy this anymore. So it's somebody bought this company, and we almost got this system. So that's why I'm really mentioning this, because we're doing our own now, but we almost got this. Unfortunately, we weren't able to get it. So yeah. So this is just another interesting thing. I only have a few more left, so we're good with them. I only have a few more, but good. Yeah. So let me. I think this is silicon carbide or something, like one of the toughest material in the world. You cannot really drill this or do anything with it.
With anything else.
Yeah. There is no way to do this in this material, because some of this silicon carbide not even conducting electricity, because they have some other process where they're using electricity to cut these holes. But literally the only way in the world now is to use this to cut this. And actually this technology, it's already on the market. This is IR laser, what they're using. So that red what you see here is not the actual laser. It's called a pointer. It's not the actual, because that wavelength you're not able to see. So the other company doing the same technology with green lasers, and that technology used to cut diamonds, the actual diamond, what they using for jewelry. Those raw diamonds being cut with a laser with a water jet. So because you need this water jet to make it straight, so you can go so deep because your laser going through the water, so it goes down into the cut. So it's just another cool. Okay, definitely. So we're gonna see some burning drones. It's gonna see some interesting thing. So Zoltan already mentioned it. Everybody heard about this. Drones, lasers. We have to shoot the drones. It's already out there. Since February, you can buy this if you have the proper papers. I'm pretty sure. IPG Photonics is a US company. We are really close. We have a really close relation with them. We using their technology. We helping them. We helping each other. We're not working in these fields. We are not that company. We're working for semiconductor mostly, not for defense. And they just released in Singapore. There was an air show in February 2026 where they demonstrated this guy. It's called IPG Crossbow. This is the system. It's on battery for 30 minutes. It can shoot drones up to 25 kilograms from 2,000 meters away. 30 minutes of battery. And I'm pretty sure you can plug it into the car and stuff, because it's not that much of a power. Because this is also fiber laser. So back on the few slides, this is also happening because of the fiber laser technology. And this company called IPG Photonics, they invented fiber lasers. Like days long time ago, there was some Russian guys also, no? Like in IPG. So actually IPG means it happened in Eastern Europe first, and then they moved here. But actually this company, so we can thank this company for the fiber laser technology. There's like also solid state laser technology, other technology, but the most common type is fiber laser, and that's thanks to IPG. There is so many companies out there who are doing this, but this is literally on the market. And if you see the stock market of IPG Photonics in February, you see the wall going up because a few videos, just some drone burning. This is some test what we did on our facility. I just want you to see the time, how long it takes to kill a drone. These drones are not flying. They just get shot by a laser beam. One more thing. Here's another wing. On camera. I want to see the IR. I mean, you see, it's a lot of damage in seconds. So you really don't have to shine that drone for a long time. Here is some IR pictures. So there's the rotor of the drone. Imagine the spinning really fast. It's spinning like 30,000. And literally 2 seconds, it's done. It's done, and you kill the drone. And in this video, this laser only 500 watt, and those what you see on the back of the truck, that's like 3 to 6 kilowatts. It's like way more power. They can focus it. Just a fasting, 3 more fast sites. So other thing, but the laser happening. So laser gyroscope. It's also thanks for the laser technology, because that's like an actual little laser generated there. This is the gyroscope. You can measure the angular momentum, and it's invented in the US during the Cold War. For what? Nukes.
Okay.
One. First ever use is the nuclear missiles, because it's impossible to jam it, because it's a light-based measurement. It's an inertial navigation system. It's literally an effect where when you start turning on one side, you're splitting the light, and on one side the light have to travel a little bit more. That's how you're measuring your angular speed. But this is nowadays is used everywhere. But it's made because of the Titan missiles in the US. They invented this thing back then. It's a 1960 concept also, come with the also some stuff. So just a quick interesting thing. They're using lasers. The submarines use lasers to communicate with satellites. It's military submarines. They're staying underwater. They're having the blue-green laser, and they literally. The blue-green laser can go through water. Infrared lasers, it's not really efficient, and so it's called blue-green laser. What they're using for these purposes, literally the submarine can shoot up a signal to the air, to the satellite, through the water, without going up, and literally there's no way to listen it, because it's a concentrated beam up there. So you have to be over it to see what's happening. So this is a communication technology what the military uses. It's public. It's nothing special in it, but it's called a blue-green laser stuff. Also UAVs. They're having the laser on the ground. They're shining the laser to the UAV. The UAV reflects back the laser, and they also insert some data into the laser beam. They adding the data. It's called the interrogation. So the drone never have laser on it. There's a laser on the ground. That's also laser thing. Your future things. This is the semiconductor laser. How brilliant is it? Like what's the density of the laser? How it's expanding throughout the air? And this is the most the transistor stuff. It's literally following the same path. Like how strong lasers are going up. Like how dense is your laser? And last interesting thing is price per watt, how it's dropping, and how cheap lasers gonna go, and this thing just going lower. So it's going to a really cheap thing in the future. That's why there's a lot of thing in the laser, and actually here's some cars up to 2030. This is all the photonics market. So this includes lasers and all the optical stuff.